Good to go.
So we're going to have a talk on CEMP-r stars and Falk Herwig. Falk is an expert in this topic and accreting white dwarfs. So we're going to hear a lot about white dwarfs in this talk. So please talk. You can start.
Yes. Okay. Great. Hello, everybody, and I'm really looking forward to this presentation.
Oops. Oh, no, sorry.
Can you hear me okay?
Yes.
Yes.
Sorry.
Okay, good. And I have been putting slides, I've been throwing in slides and kept throwing in slides, and I ended up with 50 slides. And so before I start, I have to ask you maybe to give me a little bit of a guidance of how long you want this to be. I have several sections in there that I intend to skip. And
so this is going to be like a 40-minute to 45-minute, and then 20 to 15-minute question.
Yeah. So what I will do is there will be some sections about certain aspects that, because I'm not quite sure who's exactly listening, and I'm thinking that I'm talking to the typical JINA crowd, but specifically I'm talking not to astronomers, but I'm talking to nuclear physicists who really want to get a little bit of the background of this eye process side. So that is what I have in mind. And so in that regard, I will skip a couple of slides and just tell you, oh, they are here, and then I'll leave enough time at the end so that you can decide what you want to drill in. And if you want to interrupt in between and just sort of have some questions, that is absolutely fine with me. We can absolutely have sort of short breakups and discussions of certain things. And yeah, so with that, I'm happy to start. On my screen that I'm sharing, I'm seeing at the bottom right here these controls of the Zoom. Do you see those as well? I probably not. You just see the slide, right?
No, you see only your screen. You're fine.
Okay, good. Okay, so I have put here some of the collaborators, but I have put in red really Pavel Denisenkov, who is sitting here behind me, and really to back up any questions you might have. And he has really done the majority of this work. And I didn't want to ask him when this opportunity came up to give this talk I didn't want to put the burden on him, so I felt, well, gee, I'll just do it. But I wanted to share with you a little bit the new developments that we have in this area. But Pavel is really to be credited for probably 90% of the work that I'm going to present. We also, of course, rely in this study on hydrodynamic simulations, as I will explain. And our postdoc here, Robert Endersey, and also our longtime JINA collaborator, Paul Woodward at the University of Minnesota. And we have some students here who are involved, Andrea Clarkson and David Stevens. And then, of course, all of this is enabled by the 10-year work by the Newgrid collaboration, in particular Marco Pignatari and many others. And my goal is here to give you an overview of the eye process and nucleosynthesis. And I couldn't make up my mind whether I would do this chronologically or sort of topical. And so I decided to go mostly chronological because I wanted to give you a little bit of an idea of how we got where we are and what sort of the history was leading up to this point where I think within this JINA, last couple of JINA years of research, we have really figured out something that we didn't know before, and I'm very excited about that. So I want to start with this slide here that is actually not this is from a previous talk that I gave a couple of weeks ago at an astronomers conference that was sort of dealing with hydrogen-deficient stars. It was an entire conference just about hydrogen-deficient stars in Ireland. And my talk was the only, I mean, these were the only element names other than iron and hydrogen that were mentioned in the entire conference. And this was one of my slides, and it was sort of how I'm trying to explain to the astronomer community, especially when there are lots of observers around, why nuclear astrophysics is so cool and why why we're excited about it. The elements that I put onto this chart are all elements that somehow are diagnostic tools that we have used in the past in some fashion or another of different types of hydrogen-deficient stars in the sense that we use the abundances and the peculiar, these very anomalous abundances of hydrogen-deficient stars. They look very different than the sun. They have sometimes very high overabundances of fluorine and heavy elements. We use those to constrain our astrophysical simulations of these hydrogen-deficient stars, trying to understand, how and where they originate, how these stars internally function. And so that is an important aspect for us, and an important motivation that maybe for the nuclear physicists is interesting to keep in mind, that we're really motivated to investigate these cases because there are extremely powerful tools to validate the astrophysics of the stars. And the kind of nucleosynthesis I process that I'm going to talk about here is a particularly rich environment to probe turbulent hydrodynamics and hydrodynamic convection and so on and so forth. Okay, so I took this first image and I turned it into this other image, and I put some other elements in here. And I'm asking you now, if you look at these elements, and maybe there's some heavies, but if you look at the light elements, what do those light elements all have in common? The ones lighter than iron. Who can tell me what they have in common? Come on, guys, you're a nuclear physicist.
They produce normal stars.
Think of them where they are in the chart. Think of the element charge number. These guys are all odd Z elements, okay? Nitrogen, fluorine, sodium, aluminum, potassium, these are all odd Z elements. And it turns out that all of these odd Z elements we have found are produced over the last couple of years. We have found that these light odd Z elements are produced in various types of nucleosynthetic sites in which the nucleosynthesis is coupled with the mixing. And that is also true for the I process. That's why I'm mentioning it. This I process nucleosynthesis is the result of coupled nucleosynthesis with mixing, and I'll sort of come back to that a couple times during this talk, where the convective or advective fast mixing is in the same time scale as the nuclear burning. And here's a list of different cases that we have been looking at, and the hydrogen ingestion in helium shell flashes, that is the I process side. And so that makes a couple of these heavy elements, in particular, first peak elements, second peak elements. The I process also makes these elements, this is not Lu, this is, yes, Iberium hafnium, but not iridium. Okay, so I crossed that out. Not iridium. Iridium and osmium are bona fide R process elements. We're producing just elements below in I process, but not the actual R process elements in the second R process peak. And so that is actually third R process peak. So that is really an important diagnostic that I will just give away right away. But I wanted to briefly put this I process in this greater context of nucleosynthesis simulations in convective reactive environments. And there's these examples, potassium, scandium, phosphor, chlorine we make in oxygen carbon shell mergers, the convective mergers. Fluorine and S process we make in Arca-Bohr stars. These are this is the hydrostatic evolution after a helium plus CO white dwarf merger, where these advective reactive nucleosynthesis types happen as well, and we plan to work on that. Very interesting nucleosynthesis there. 2-dex enhancement of fluorine. And then we have sodium and aluminum being the hydrogen-helium shell mergers in top 3 vessel stars as well, but we're not going to talk about that today. Okay, so I process as one flavor of an emerging general scheme of convective reactive nucleosynthesis. And you know, the way to think about this is that you have these different layers of isotopic charts. And normally we look at nucleosynthesis pathways in one of these charts. But if the mixing takes place on the same time scale as the nucleosynthesis, then we can have entirely new nucleosynthetic pathways, because suddenly, so these green vertical arrows are sort of the mixing, and you can see the mixing has different time scales at different depth maybe, but then also there's reaction time scales that are certainly different at different temperatures, and how these are interacting. It is like giving your nucleosynthesis chart that can do nucleosynthesis in one chart of isotopes. It's like giving it another dimension, okay? And that's why we think of the convective reactive nucleosynthesis as nucleosynthesis with an added dimension, and the added dimension is the mixing, okay? So what you have is that you're producing something in some location, and if it were to stay at that temperature, nothing interesting could happen. For example, we produce carbon-13, or we produce nitrogen-13, nothing interesting happens with nitrogen-13. But it decays, and while it does, it can travel to a very high temperature. And there, it decays maybe to not carbon-13, and at this high temperature, the carbon-13 actually can do something on this convective time scale. Okay, without the mixing, it would be dead, but with this added component connecting different conditions, we have entirely new pathways to create elements. And that's sort of what this whole convective reactive nucleosynthesis is about. And I process is one of these key examples of the convective reactive nucleosynthesis. And so that is a key concept. And so I wanted to explain that right away. I will sort of go a little bit faster for the next couple of slides, because they're not key nucleosynthesis, but they provide a little bit of interesting astronomy background and context. So there is a very, especially for these rapidly accreting white dwarfs that sort of have come out of nowhere in terms of nucleosynthesis due to I mean, this is really very new, but it relates to stuff that has happened over the last 20 or 30 or longer years. So I wanted to just give a little bit the astronomy context of where is this idea of the rapidly accreting white dwarfs and their nucleosynthesis isotope, where is that coming from? Okay, and so hydrogen fission post-AGB stars are a class of stars that have been investigated for 20, 30 years, and we see on the left here something that is similar to a Hertzsprung-Russell diagram, except it is log G, the surface gravity and temperature. And you can plot your solution tracks. You can see sort of this knee-like structure that you also see. I think I can't point on this, but that's okay. I have to just describe it. On the right side of the diagram, you can see the...
You can use your mouse.
Oh, you can see my mouse? No,
Oh, no, sorry.
No, I can't. I can't use the mouse, unfortunately. Anyways, so you can see this location. These are hot stars. These are located where the central stars of planetary nebula are located. And in the right diagram, you can see the same structure in the Hertzsprung-Russell diagram, you see the asymptotic giant branch on the right, and then as the star is evolving away from the asymptotic giant branch star to the left, it is getting very hot and still luminous, and then finally it turns down to become a white dwarf. The question is, how do these hydrogen-deficient stars evolve or form? And one very interesting aspect of these is that actually they have a lot of helium. These are some observational results. There is a 30% mass fraction of helium. These are individual hydrogen-deficient stars. And also, they have significant amount of oxygen, 10% by mass. And this is measured at the surface, and they have no hydrogen. So you clearly must be looking somewhere deep into the nucleosynthesis, deep into the inside of the star, where the nuclear physics processes would have happened. So the idea was, and this is sort of a very old idea going back to the late 1970s and early 1980s, is that a final helium shell flash could happen when the stars have already become a white dwarf. And this helium shell flash would lay bare the interior zones of the star that have no hydrogen, where all the hydrogen has been burned. So what would we be seeing if we go there? So here are these helium shell flashes in the Kippenhahn diagram. You've probably seen that. They're the pulse-driven convection zone. And it's really terrible that I can't point at this. And you know what I'll do? I think what I'll do is I will go out of the full screen mode, and instead I think I'll do this because this way I can point at this, and I think that is probably more important than. So I can make this larger. Okay, how is that? Can you see things okay this way?
Yes.
Yeah?
No.
Yeah?
Yes.
Fine.
Okay, because this way I can point, and this way I can point, and that I think is much more important. Okay, so these are these helium shell flashes, and you've seen these Kippenhahn diagrams before, evolution as a function of time. What is important here is that we have a helium-free core, we have a hydrogen-free core, and this is really zooming into the middle of the star. And so the question is, when we see a lot of helium and a lot of oxygen, where would we be looking? Now, here's a diagram that shows the internal profiles. And at the top, we have here we have the profile of the entire 2 solar mass star. There's a big convective envelope on the right. And here we're zooming into this region around 0.6 solar masses. And what you can see is that if you go from the outside into the star and you go into where there's no hydrogen, there is indeed a zone here, which is this labeled intershell. And it has a lot of helium, oxygen, a few percent, 5 to 10%. It has lots of helium, and that is the helium burning layer. So somehow, in these hydrogen-deficient post-AGP stars, we're seeing into the helium shell of the progenitor AGP star. That is the notion here. Okay, so we were very fortunate to observe 20 years ago so the idea is, I should go back one more time. The idea is, how do these form? The idea is that here's this Kippenhahn and this HR diagram. You have the post-AGP evolution. This is normal post-AGP evolution here, this red line. But then offset, you can have a case where these thermal pulses happen when the star has already left the AGP. So they happen here in the central stars of planetary nebula region. They would then be thrown back because of the energy input to the red giant branch. And as they come back, actually, they would inflate, and there would be mixing of hydrogen into the helium shell phase convection zone. That would further boost the nucleosynthesis, and we would get back to the RGB. And the cool thing is that we have captured one of these stars in the 1990s. It's called Sakurai's object, and it has very, very peculiar abundances. I want to point your attention in particular to these abundances of 4 dex, 3 to 4 dex enhancements of first peak elements, strontium, yttrium, zirconium, compared to, sorry, 2 dex enhancement compared to solar. So this is a very unusual, abundance structure, and it is shown here in the right. You can see in black the overabundances of yttrium, strontium, zirconium, and in red we see models. And interesting about the star is that the second peak elements, garum and lithium, are not enhanced. And so you can see that in this model, our initial model based on 1D star evolution simulations, we were not able to reproduce in our model, which are the red stars, these very large first peak elements. This is log, so this is a 2-deck enhancement. And we trace this problem to the fact that in 1 dimensions, you're really not able to track the entrainment process into this, the hydrogen entrainment into the helium shell correctly. This is what happens when the thermal pulse happens on the post-AGB star. The convection zone expands to reach the hydrogen-rich envelope. And in the top right, you can see this purple line. That is the hydrogen in the profile coming down, but it cannot reach the further down because in 1 dimension, the convection responds by creating a mixing barrier. At the left, we see the hydrodynamic picture where this is very inhomogeneous and not like in 1D, and we can have lots of mixing going down into deeper layers. And so we created a 1-dimensional model that was inspired by this hydrodynamic simulations. And you can see that we are now able to produce the first peak elements pretty close to how they are observed. So how did all this happen? How does this happen? So the general idea is that we have here a schematic picture. We have on the left the helium shellfish convection zone stable layer above. And the idea is that in these simulations, we have protons being ingested, and then the protons will react with carbon-12 and produce nitrogen-13. And then that nitrogen-13 will mix further down to the bottom of the convection zone where it decays to carbon-13. And then at these high temperatures, there's very fast carbon-13 alpha N production, neutron production, and that produces very high neutron densities. I have now a couple of slides where I'm showing hydrodynamic simulations that we created after we realized that this was a hydrodynamic site. And they're beautiful simulations, and if you're interested in the hydro, this is the vorticity. I would be thrilled to discuss those with you in more detail. The important point is, this is the vorticity of the shell, and in the center you see the inner white dwarf core. I don't know how well this comes through on your screen. The important point in these simulations is that as we're going towards later phases, oops, sorry, I should go to this simulation here. Oops, I'm going to go to this. No, I go to this simulation here. This is a very similar simulation. I show it because it shows some of the features very nicely. This actually happens to be, oh, why doesn't this go? Can you at all see this movie on your end?
Yes.
Okay.
I think it stops because it tells me that it can't transfer fast enough, so I have to keep restarting it. I think it is sort of a matter of how fast can I move it forward. And I will accelerate a little bit here. So this movie is actually from a hydrogen injection simulation in the low-Z AGB star. You see at the tails of these mixing, you see the energy generation. These are these red blobs. The important thing that I want to show you at the end is that this kind of configuration is really blowing up in a very violent global oscillation of shell hydrogen injection that you can see now. This is the fractional volume that we're seeing, and the entrainment are these different color scales. And this is a simulation that goes into a totally different state. And at the very end, you can see it to become very violent again, and really blow up in a very non-spherical manner. Our hydrogen injection in these pulse-AGB stars does the same. And in 2014, there was a paper where we published this, and you can see this GOSH in various diagnostics, for example, the maximum convective velocities. So that is sort of a problem because we do not really know how the detailed nucleosynthesis works. There's a little bit more about the hydro that I will skip. But I will show you what you might find most interesting, a movie here of the nucleosynthesis from our one-dimensional simulations. Oops, sorry. Let me to control this here. So what we're showing here is our one-dimensional simulation where it is not correct because it does not include these very violent oscillations. What we're just saying is we must be able to continue this hydrogen ingestion. And so you see a version of this convective reactive nucleosynthesis. Here in the left, you see the hydrogen being ingested. This is this line here. Oops, I'm sorry. I need to find a good spot here. Okay, so here maybe. This is, sorry. Okay, so the hydrogen comes in. This is this blue line here. We have the carbon-13 form, and you see all of this is convective, but we have these profiles in the convection zone. So the nitrogen-13 forms where the hydrogen goes down, and then further mixing brings the carbon-13 down to the bottom where it is very hot, where the neutrons are released. And the right scale here shows the neutron density, which reaches 10 to the 14, for example. And then you see, for example, production of lithium, beryllium-7. And on the right, you see these profiles of all of these heavy elements being formed. And you can see how their values go up. And if we wouldn't let this go for long enough, they would go up for a very long time. Okay, so this is the eye process in the saccharized object, and we were able to this is sort of the idea. This is the simulations behind these models, and all of this is in a single star, in a single hydrogen deficient star. Sorry, in a single post-AGB star that has become hydrogen to one of these helium shell fletches with hydrogen injection. Okay, so so this is this eye process, and here I'm just showing in one slide how it differs. This intermediate process differs from the more well-known S and R processes. The S process, of course, follows along the value of stability very closely. Actually, in the chart, it's very boring. The R process, you all know, sort of goes way off. The I process is sitting at a neutron density of 10 to 15 per cubic centimeter, and it sits at sort of 5 to 6 off the value of stability. And it goes through sort of here things like iodine 135, it goes to krypton 89, and other things. So it is not as extreme as the R, but it does clearly go several mass numbers off the value of stability. Okay, so now I want to come to the rapidly accreting white dwarfs. And the rapidly accreting white dwarfs are actually very similar to these hydrogen, to these post-AGB stars. They start out So the idea is that we have a binary system where one star evolves to become a white dwarf, and the companion, initially less massive, evolves later, and as it evolves, it gets into a situation where it can donate mass to the white dwarf, and the white dwarf will be accreting. Think of it, it's very similar to a nova, except that this is a situation where we're accreting at a much higher rate than in the nova. In these rapidly accreting white dwarfs, we have a configuration where we're accreting at such a high rate that the hydrogen burning is sustained from the accreted hydrogen. Okay, so we're accreting at the same rate as the hydrogen burning would proceed, and this is a style evolution track of the progenitor. Then there's a nova phase that Pavel includes in order to smooth. It's very short. It's just sort of to ramp up the accretion. But the important part here is this green part, where you can see where there's these multiple loops, and each of these loops are not as a nova. They're not hydrogen shell flushes, but instead they are helium shell flushes, because as the hydrogen is accumulating, there is helium accumulating, which is the hydrogen burning ashes. And as the helium is accumulating, ultimately it behaves exactly like an AGB star, except on this accreting cold white dwarf, and it does thermal pulses. So these helium shell flushes in rapidly accreting white dwarfs are thermal pulses, okay? So an interesting result of this was that what the mass retention rate is, and I will skip that, it makes for high metallicities supernova type 1a pathways unlikely because the mass accretion rate is small. But another difference to these post-AGP stars is that the entrainment process, the hydrogen entrainment process is more stable. We do not see these violent explosions even in 1D, the split of the convection zone that we saw in our helium shell flash post-AGP simulation of single stars. And the reason for that is, so you see here at Kippenhahn diagram, it goes on for almost a year at the bottom here, and you see the hydrogen burning luminosity, the helium burning luminosity, and all of this is relatively well behaved. You have a continuous entrainment that goes on for a long, long time. And the reason why this is the case is because these white dwarfs are cold, much colder than the young white dwarfs in single post AGP stars. So we understand why this is happening. But what it means is that it really provides a different environment for nucleosynthesis. We see in these helium shell flashes on these rapidly accreting white dwarfs the hydrogen ingestion. And we can follow it in our one-dimensional simulations to a relatively good degree of accuracy. So this was published by Pavel and our group a couple of years ago. And since then, Pavel has marched ahead and calculated an entire grid of for different metallicities. And so essentially calculated yields for these I-process stars. For this rapidly accreting white dwarfs, all the way down to FeOVH minus 2.3, and I think there's minus 2.7 as well. So covering 5 metallicities. And so with this yield set, the question is, what can you do with this yield set? There are some very interesting details that I don't have time to discuss. One of them is that these yields were informed by our hydro simulations in various ways, through the entrainment rate and through the connected boundary mixing. So that you would have to read about in the paper, that these yields have been informed by our hydro simulations of rapidly accreting white dwarfs. So calibrated, so to speak, and here are the results. For different metallicities, you can see here on the left, the neutron density, and you can see that the neutron densities reach higher values for the lower metallicity models, and that is simply because there's less seed. Okay, so we can understand that if there's a certain primary source of neutrons and there's less seed, then the neutron density is higher. Interestingly, for solar-like metallicities, the entrainment can be, the neutron density can be as low as the highest neutron density seen in the canonical S process. So this is an I process is bordering at the S process. In these low metallicity models, you do sometimes see peaks of neutron density at the very end. Very interestingly, here is the, I will make this a little bit larger for you to see better, is the, are the abundance distributions. And again, this is sort of for model A is the highest metallicity to model F is the lowest. This is sort of a behavior in the overall, this is basically showing the neutron exposure, right? So for high neutron exposures, we're going to the second peak and third peak, and we reach these high neutron exposures again where we have small amounts of seeds at very low metallicities. But at low metallicity, at higher metallicities, we have lots of iron, lots of seeds, and the same amount of neutrons that we produce do not get as far. So generally speaking, the actual rod models are not that different depending on the metallicity, but this is really a simple metallicity effect, and you can make similar plots for S processes. It works very similar. So this is a familiar behavior. Now, what can we do with these simulations? Well, we can apply our galactic chemical evolution pipeline, the JINA galactic chemical evolution pipeline. And in this paper here by Benoit, we have investigated the contribution of these rapidly accreting white dwarfs to the solar system first peak element distribution. And that was motivated by this old idea that we might need a lighter element primary process for the solar first peak elements. This is a galactic chemical evolution paper that sort of is informed by stellar population synthesis. And what I wanted to highlight here also is that we include errors. And you see in this, the green is the abundance prediction, the black is the solar. You see these blue errors. These are the nuclear physics errors, and I'll come in a moment to where they come from. The red are astronomy modeling errors. Sorry, the green, okay? What else can we do with these? So this is iProcess may have a signature in the solar system contribution of first peak elements. That's sort of one takeaway message. The iProcess in this higher metallicity rapidly accreting white dwarfs. What else can we do? And this is where we come to the CEMP-r stars. I don't have to introduce CEMP stars in this forum a lot, but I will show you here one of the best representations in this model, where you start with a previously R process enhanced cloud, and then you add the S process from a AGB star on top of that. And what you see is that there's a fundamental problem with this. If you add R process, you will add iridium and osmium, which are, as I mentioned, real third peak element, R process elements. And that limits how much you can put. And you are having real problems reproducing the range erbium to hafnium. So the key signature of the CEMP-r stars is their high hafnium, lutetium, iberium abundance relative to the actual real osmium, iridium, also rhenium abundances. And these models are not doing a very good job in being able to reproduce this. So can we do this better? Yes, we can. Here is a movie that is showing you our latest 3D 1D nucleosynthesis approach, where we're doing rapidly accreting white dwarf hydro simulations on the left. We're taking out nucleus diffusion coefficients from the hydro. We're post-processing this in 1D. And at the bottom, you can see as the simulation approaches, how our iProcess simulation approaches very nicely the observed abundance distribution. And I will show you our best fit model right now in the next plot in large. This is Pavel's rod model G, and it shows you that these rod simulations at low metallicity can relatively naturally reproduce the entire mass distribution from carbon all the way up to the heavy elements and even to lead. And this is only possible because we're doing multi-zone simulations. Other simulations, for example, our earlier simulations by Dardelli and also those by Humpel, these are single zone simulations, which for numerous reasons that we can discuss, cannot reproduce the entire abundance distribution like this. What I find very exciting is that, yes, there are still some hiccups here, but overall, first of all, note here the very good reproduction of the hafnium, thallium to osmium, iridium abundances. This comes naturally out of these simulations. And also lead and iron and all of this stuff, carbon, all of these things come out just absolutely fantastically. You can see that I'm excited. The reason why I'm excited is that in these rapidly accreting white dwarfs, we're actually not having a lot of free parameters. I'm saying here these are essentially parameter free, and there is no parameter free simulations, of course. But what I'm meaning by that is that we do not have to make a lot of ad hoc assumptions. These are straightforward stellar evolution calculations that anybody can do. This is 1D stellar evolution, and the entrainment apparently is relatively well described, plus minus details that we're now figuring out with our 3D 1D approach. But there is nothing unusual that we have to do. This just comes out. If you run your stellar evolution calculation, run the 1D nucleosynthesis networks, it comes out. So I think that that is really a very strong result. And you know, and we really do believe that these are that this is sort of the site for low metallicity, for these low metallicity CMP-r stars, for those CMP-r stars that are showing the eye process signatures. Not all do. I have to emphasize that there are CMP-r stars that are not CMP-r stars. Okay. All right. We're running out of time, and I have here some slides that describe in more detail the actual convective reactive nature of the nucleosynthesis. And you can see here these different levels of the nucleosynthesis charts and how they interact and where what happens. And I would be happy to discuss those in more detail, but I want to spend the last couple of minutes in order to talk a little bit about the various impact studies that we have done. And so if you just give me a couple more minutes here, I'll summarize those, and I will be happy to discuss that in more detail if you wish. The first study, so our approach to this is the following. We are starting with an observed abundance property. And in this particular case, in the first study that we did, that was the abundance of Sakharai's object, the abundance of Sakharai's object, which you can see in this middle diagram here. I'm trying to make this a little bit larger, which you can see in this diagram here as these black dots. And then we take multi-zone simulations of the type that I just showed you with these 4 panels. And we are running those, we're identifying the flux that feed into these particular elements. And then we have gotten from Georgios Paridakis at MSU, we have gotten from Hauser-Feschbach calculations estimates of the uncertainty for the N-gamma cross-sections. And we feed those as weights into Monte Carlo simulations where for about 50 or so N-gamma cross-sections, we're pulling randomly realizations, and then we do 10,000 full multi-zone simulations with large networks. And that is now eminently doable. So these are Monte Carlo multi-zone simulations, 10,000 realizations, and then we put here, we pull out a distribution. And so you can consider this sort of the nuclear, these little colored error bars, you can consider those the nuclear physics uncertainty. And there is a number of things in this plot that I want to highlight. One is that the nuclear physics uncertainties in this environment are as large, approximately, or actually very similar, the 1 sigma. If you fold it into 1 sigma, and that is done here, if you look carefully, there is these 1 sigma error bars here. They're as large as the observational errors. Okay? So this is really important. The nuclear physics uncertainty, we will not be able to really advance and figure out how this all works and use, as we wanted to, these sort of exotic sites for constraining physics, astronomy, learning about this. With these error bars, we're sort of at the end of almost of what we can do. This is the same as the observational error bar, which needs to be improved. The other is that we see some actually quite funny features. Like, for example, you see some nonlinear behaviors here sometimes. And so I'll get to that in a moment. This is published, Journal of Physics G article. You can read it all about it. There is sort of the correlation factors, coefficients of these different elements. And here are the different reactions that have the largest correlation factors, krypton 89 and so on and so forth. And so you can read all about this in the details in the paper. As an astrophysicist, I really like this diagram, and so this is sort of making, again, the point of these uncertainties. Here, just for the case of zirconium, we're showing the observation value in gray, and in green is the theoretical value with the nuclear physics uncertainty. And the gray is sort of an interpretation of the 1 sigma error given as sort of a Gaussian. And you can see that although the actual measured values are maybe 0.9 and 1.9 dex, if you show this diagram to a high energy physicist, within 1.5 sigma or so, these two things agree on this log scale. Okay? So that is really an important message, that without constraining these errors better, we have difficulty distinguishing between models and observations by better than 1 dex, which is a lot. It's a fact. Well, okay. So I guess you get the story. Okay, so this is a slide just to remind you that there is an experimental program going on, and this Artemis gave me this slide. I just wanted to throw it in here, and then we can discuss this more. There's an experimental effort underway now to address some of these things. I want to briefly mention 2 new uncertainty studies. This is
you have like 1 minute.
Yeah, 1 minute. This is an uncertainty study that is in prep. We can share with you the preliminary results on the second peak elements. So this is for the CEMP-r S-stars. And again, we can see in some cases these nonlinear relationships. And we have for the second peak now also these uncertainties. Again, they are similar to the observational uncertainties. We're identifying super branchings, such as iron 135, where the entire distribution can be split into 2. Very interesting. These are the very, very most important. And the last thing in the last minute that I want to mention is that we're also now doing a weak eye process uncertainty study. There was a paper by Herwig from 2006 where he was looking at supersolar arsenic to germanium ratios and enhanced molybdenum lutetium, which were interpreted as eye process. And we're just finishing up a new impact study in that, for that light element region as well, between iron and the first peak, specifically focusing on arsenic and germanium. And so these are preliminary results that are available as well. And that's it.
Thank you so much. So let's see. If anybody has a question, please write it in the message so I know how to queue people.
But I will start with my own question. What is the, so in order to explain the frequency of CEMP-r stars in the Milky Way's halo, so there should be a frequency of accreting white dwarfs in the accretion history of the Milky Way. So from population synthesis models, do we have enough of accreting white dwarfs to explain the number of CEMP-r stars?
This is a very good question, and that has not been answered. We do have in the Cote et al. Paper, we did do population synthesis calculations to feed into the galactic chemical evolution models for the solar LEP contribution of I process to the solar system. And sort of the numbers are in there, but we have not done that analysis yet. So I cannot answer that question, but it is a question that definitely will be answered and can be answered. It's straightforward to answer.
Okay. Okay.
Have we estimated this better?
I think we estimated the rate of growth of performance.
Yeah.
But I'm not suggested.
So we have the numbers that are in there, but we haven't really had time to answer that question. Yeah, but the numbers are there.
Okay. Anyone else? I haven't received any messages, but feel free to unmute yourself and ask questions because I didn't see any messages from people who didn't join the conference. Some clarity. It was a very hard topic to digest for people. So.
Well, I understand, and that's why I felt like we have been talking about this at JINA Frontiers meetings, and so this is why I thought I would take the opportunity to try and explain a little bit more of the background of where these simulations come from. But I think that one of the main messages here is that we're having 3 impact studies now that the results are in. We're just writing up and checking everything, covering weak eye process. First results here from the weak eye process study is that nickel 66 may be very important. We're identifying those species. I mean, you could see, if you think that, if you look at this chart that I had here of the eye process in this diagram, right? If you look at the chart, you might think that, oh my God, you have to measure everything. And it turns out that in this approach that we have, where we look at specific examples of specific observables, and then we're doing an impact study where we're asking what influences that observation. In all of these 3 cases that we have done, for first peak, for CEMP-r stars, and for weak eye process, we always find less than a handful of N-gammas that are really important. And I was really relieved to find that, because it means that the nuclear physicists really have a fighting chance to focus on this relatively small number. You do not have to measure all of these N-gamma class sections.
So we have a question from Jay Woon and ask, are the accreting white dwarfs the only candidates for eye process, or are there additional?
Now, this is an excellent question. So I actually had a slide here at the end where I have listed the eye process environment and observables that I haven't really talked about. So there is evidence in the observation literature. People have observed barium to lanthanum ratios that are much higher than what you can get from S, and so also from R culture. And so there is there's a minimum of the barium over lanthanum that you can get from R process, and a maximum from S process. And in principle, in this recommendation, all barium over lanthanum ratios measured in the universe have to be between these two levels if there is only S and R. I processes have been predicting higher barium to lanthanum ratio. And there are observations in open clusters, which are high metallicity environments, that show significantly enhanced barium over lanthanum ratios. And this has been tested, this has been checked multiple times because it is so unusual. And so far, our process is the only explanation for such high barium over lanthanum ratios at high metallicity stages. So I cannot see a way to make these heavy second-peak I process elements. Right now, I do not have an astrophysical fide for second-peak I process elements at high metallicity. In the rods, ultimately, we get to the second peak because we have a low seed number of seeds, right? So the neutron exposure is high. But this observation is either wrong or it suggests that there must be other sides. From a theoretical point of view, there's a couple of sides that have been discussed. In a paper with Sam Jones, we have suggested that super AGP stars could be a site. There's also a possibility that low Z AGP stars or helium core flash is a site. So the helium core flash could be, in low mass stars, could be mixing hydrogen into the helium core flash and then do this thing. There's also a possibility that hydrogen helium mixing takes place in massive stars. And the top 3 model that Andrea Clarkson suggested, it is one possibility, the light eye process and massive stars.
Let's ask the final question. So we have a question that says, why are the error bars on your slide 45 very small compared to other plots that you show?
Slide 45. Which sorry?
So yeah, they say that so they think that the stars presumably have error bars that are too small to be compared. That is how I understand the question, but they can clarify. It's from
this is the nuclear physics uncertainty. Okay, so this diagram says that if you are taking the uncertainties that we received from MSU and you run them through our Monte Carlo multi-zone simulations that I just showed you how well it reproduces the observed star, this model here. We do this 10,000 times, and then we're pulling these uncertainties. And then these color bars here show the Monte Carlo nuclear physics uncertainty. Does that answer the question? And it is as large as it is because that's what the nuclear physics uncertainties are.
That's true. Well, we are at the end of our 1 hour allocated time. Thank you very much, Falk. This was amazing. I learned a lot. I hope other ones also did. So we will have the next meeting in 2 weeks. So please join us. And I think we can say goodbye to Falk and hopefully see you in 2 weeks. Thank you again, Falk.
Okay, great. Thank you. Bye-bye.
Bye.